All right, started recording. Today we're going to have a new chapter. A new group of chapters. So the first chapter will be chapter 4. So we will cover some new material today. If you look at the big picture over here, this big picture shows the diagram of our control system, PID control system, the controller. We studied this semester will be a PID controller. And this PID controller need started with a sensor. So that's today's subject. And then we will go to the control elements. Then we'll go to the PID controller. So today we will start the 4, 5, and 6. 3 chapters, chapter 4, chapter 5, and chapter 6. And then we're followed by the control element, which will be chapter 7. And last, we will study the PID controllers, chapter 9, 10, and 11. So that's our plan. Today, we're going to get started with the first sensor and the most important sensor, probably. Every sensor is important, but this one is everywhere. Around your house, in the chemical plants, any factory need to produce something. One thing you need to control is temperature. That's a temperature sensor. We will cover 4 different types of temperature sensor, plus 2 extra. So altogether 6. So I will go like this. We will cover 6 different types. Number 1. Number 2. So we'll talk about that in detail. Number 3. Thermocouple. Number 4. Solid state. Number 5 is bimental. Number 6 will be whatever this is generally not considered a sensor because you need a human operator to actually interpret the readings. So a machine generally is not used to read those meters. That is the meter. Some of you, when you measure your temperature, you use one of those, gas or liquid or vapor. So we will talk about all six. Of course, those are probably the first 4 are most popular. The first 4. So let's start the first one. The first one called RTD, temperature sensors. R means resistance. T means temperature. So resistance, temperature, detectors. So this detector is a resistor. If you know resistance, if you study resistance, the resistance always changes with temperature. So that's the physics. Resistance change with temperature. And that can be used as temperature sensors. So we will go through a couple of categories. First is the sensitivity. Sensitivity of this type of sensor is not very good, actually. It's like a 0.4% per Celsius degree. So if your environment, the temperature changes, there's only 0.5% of change of resistance. 0.5%. So it is considered not very sensitive. Yeah, 1 degree, only 0.5%. But with the right circuit, we still can detect that change. So that's the sensitivity of the first issue. Second is the time, response time. So how fast is the response time? It's a couple seconds, like 5 seconds or 1 second. So in seconds, so that's the response time. If you want to get an accurate reading from this type of sensor, you'll probably have to wait for 5 seconds or more for that sensor to get stabilized. So sensitivity, 0.5% per degree of change. Response time will be about a couple seconds. Next is the construction. It's usually very solid construction. Have a stainless steel jacket. So I have one of those. This is my sensor, and by looking at this sensor, you know it's really that's the sensor. So that's the construction, and it's very nice. You can screw it, put another bolt on top of it, and holding it into the where you want to measure temperature, ovens generally. So it's like a pencil-like device. It almost looks like a pencil. The next topic will be signal conditioning. That is, how do we interface? Generally, we use a bridge for interface because it's a variable resistance. So that will be our sensor right here. So if you notice the bridge, we have 1, 2, 3, 4 resistors. This 4 resistor will form a bridge. And the RTD sensor right here. And that will be the signal conditioning circuit plus the amplifier. You need 1 or 2, maybe 3 amplifiers to reconditioning your signal. So your signal will be in the right range. Typical controller, for example, want 0 to 5 voltage. You want to reconditioning your whatever resistance. For example, your resistance changes from 100 to 150. If your resistance changes from 100 to 150 when temperature changes, you want to design your circuit, whole circuits. So the output here will be 0 to 5 voltage, 0 to 5. When resistance change from 100 to 150. That's signal reconditioning. So a bridge plus amplifiers. Bridge plus amplifiers. That will be the signal conditioning circuit. And some of you may wonder, how do I design those amplifiers? Actually, the computer can do it automatically for you. You don't have to. Let's do one of these examples. So in the example part, we also give a couple examples, and you might wonder, where did they came from? Where did they came from? That's the sensor. And that's the signal conditioning circuit. 1, 2, 3 amplifiers right here. So actually, the whole design process, computer can do it for you automatically. So of course, if you electronics, you want to know more about it, you can study the whole process. We have many electrical circuit classes, 212, 312. In that courses, you will learn how to do it in greater detail. But anyway, as a technician, for example, you're on the job site, you probably want to use a computer, or when you design the circuits, design system. The computer will do it for you perfectly, okay, not a problem. That will be your sensor, that will be your bridge, and the output will be whatever required, 0 to 5 or 0 to 10. So that's our next subject, signal conditioning. We need a bridge plus amplifiers. The next topic will be dissipation constant. That's another topic we always want to find out. Dissipation constant. What exactly do we mean dissipation constant? What we mean is how much self-heating it will create. For example, if a dissipation constant is 225 milliwatts per degree of Celsius, that means for every 25 milliwatts, the sensor will self-heat itself. If you look at a typical circuit, this sensor is energized through a battery. So the battery will provide power. The electric current will go through this sensor. That means some kind of power will be consumed on the sensor. So if we go through all this process, if this is 5, this is, for example, 30 milliwatts is up there. So suppose with a 5 watts battery, 30 milliwatts will be consumed here. If we have 30 milliwatts, the dissipation constant is 25. So it will be 30 divided by 25 equal to 1 degree, almost 1 degree. So the sensor will be 1 degree hotter than the environment it's trying to measure. So if your room temperature is Celsius, 72 Fahrenheit will be 20 degrees Celsius. So if your temperature is 20 degrees Celsius, and your sensor is actually measuring 21 degrees Celsius, where's 20 plus 1? 20 plus 1. So that's dissipation constant. Say if another sensor dissipation constant is 15 milliwatts per degree, the second sensor will be 2 degrees above. So let's say you buy 2 separate sensors. The first sensor, room temperature is 20 degrees. The first sensor will measure 21 degrees. The second sensor will measure 22 degrees. Why? Because it's self-heating. The sensor will warm up by itself because it's energized, it's powered. That is the problem. I actually did one thing around my house, measure temperatures. It's a wireless temperature sensor. Then the reading will be uploaded to the cloud. That's a project, I forgot the name. I did it a couple of years ago. That's a very good project because it turned out millions of people did the same project. What happens if millions of people did the same project and upload their temperature readings, including GPS information, including locations, up to the cloud? That means everybody can read the temperatures anywhere in real time, free. So you got millions of sensors around the world measuring whatever. Can be temperature, can be humidity, can be wind speed. Then all the data collected by those Internet of Things, it's called the Internet of Things. All their data is uploaded into a central location, which is free to the public. So they were predicting the Internet of Things will goes up 50 billion in a couple of years. 50 billion. So if those 50 billion Internet of Things, they all measure everything, your speed. When you're driving a car, your cell phone actually is measuring how fast you drive in real time. And believe it or not, they may upload that speed information with your agreement. You agreed probably somewhere when you download the app. You said you have to agree this, agree that, and you even didn't read it. You just said agree, agree, agree. Anyway, those billions of Internet of Things, all their data, if they are all loaded into a central location, that became very powerful data. So that's what they try. Anyway, dissipation. What is the last one? Let's do one more. That is the last. Oh, last one is range. So what is the range of this temperature sensor? It's 100 degrees, 100 degrees. So for example, negative 100 to positive 700. So that is probably the range of the temperature. So, what about above 700? Above 700 is too hot. That RTD probably will melt it, became unstable. So less than 700 degrees Celsius. This probably translates to 1,000 degrees Fahrenheit. I didn't do the math, but you can change conversion. Anyway, this is Celsius. Okay. So this will be our first sensor, RTD. And we covered 1, 2, 3, 4, 5, 6, 7. So we will continue to do second one, third, fourth, everything. We will follow the same style.
What's the column that's empty? What's the title of that?
This is construction.
Oh.
Construction will be steel. I will maybe put a steel construction over there. Yeah, steel jacket. All right, thank you, Tim. Yes, have any questions? That's why you are here on real time. Otherwise, it would be perfectly okay. You just watch videos, right? Because you are here in real time, anytime you have a question, please ask. Without the interaction, it's no good. In order to make it work better, we need more interaction, the better. I know some of you at work can talk, but a lot of you are at home. Let me know if you have any questions. All right, that's our first one. Let's keep moving on to the second one, called the thermistors. Thermistor turned out is another resistor. So these two are both resistors. What's the difference? The difference, this is the positive temperature coefficient. This is the negative temperature coefficient. That's the difference. The material is different. Constructed by different type of material. The second type is constructed usually semiconducting material, some kind of ceramic baked together. So there is a recipes to bake a thermistor. It will be negative temperature coefficient. What does that mean? That means as temperature goes up, the resistance drops. So the resistance actually, unlike previously, the resistance actually goes up. Previously, the higher the temperature, the higher the resistance. That's why I call it a positive temperature coefficient. It has a positive temperature coefficient. The second resistor, the resistance also varies, but it has a negative temperature coefficient. The resistance actually drops, decreases. So that's how it looks like, negative temperature coefficient. The vertical is resistance, the horizontal will be your temperature. And notice how sharply it draws the temperature, the resistance actually drops. So first thing is sensitivity. Up to 10% per degree. 10% per degree. So it's extremely sensitive. If you look at here, you'll notice it's very sensitive. The faster it drops, the more sensitive it will be. So it's extremely sensitive right about here. As temperature increases, it's less sensitive. So it's better to measure temperature in this range. This is the perfect range, best range. This will be okay, but not as sensitive. But this is the most sensitive range. Most sensitive. And a couple of seconds. Almost all these temperature sensors need a few seconds of delays. So seconds. Because you are measuring thermal energy. When you are trying to measure thermal energy, you need that energy to actually conduct. It takes a while for the thermal energy to conduct through the sensor to the sensor. Construction is less tough. Yeah, you can protect it, but it's a kind of ceramic type of material. Unlike the previously is made of alloy, some type of alloy, so it's very tough. Unable to break it, very hard to break. But it's okay construction. It's ceramic discs. Yes.
You meant metal alloy.
Alloy, yes. Yeah, the first one is alloy, yes. Some kind of combination of metals, yeah. The second one is not alloy, it's a baked ceramic type of material. Yeah. It's beads, rods, and discs, about 1 millimeter in diameter. So that's how it physically looks like. The author goes to the range next. The range will be about negative 100 to 300 to positive 300. So the range is less. It's obvious because that ceramic cookie you baked or semiconductor device you baked cannot handle higher temperature. Another reason may be this: as temperature goes higher, it's less sensitive. So anyway, the range is about half. So if you measure 300 Celsius, it's okay. Response time, half second. Seems a little bit better, so I will put it there. Half second. That's what the author put it there. So this is up to 5 seconds. So it's like half to 5. So the first one is anywhere. This one I would think it will be identical. So I don't think there's a big difference in the response time. Typical 10 seconds. So it's the same, half to 10 seconds. Okay, so response time will be half to 10 seconds. All right. Half to 10 seconds. signal conditioning can be the same as previous. Actually, you can save a bit of money by only use one resistor. That means use this. So only use two resistors instead of bridge. So we can, that's where the sensors are. Oh, that's where the sensor. This will be your sensor. This is another resistor. So signal conditioning can be simpler than previous one. If you want to save a couple of resistors, simplify. Why? Because this sensor is very sensitive. It has 10% of change per degree. So think about it. 10% of resistance variation per degree, up to 10%. You have very dramatic resistance variations here. So you can afford to not use a bridge. Bridge are more sensitive. They all get the job done. That is converting this resistance variation into voltage variations. So signal conditioning will be this plus amplifier. Now you still need amplifier to make it. The previous one preferred a bridge plus amplifier because bridge is more sensitive to convert variable resistance into variable voltage. The second one, because the sensitivity is huge, 10%, so we can simplify. That means we just use a voltage divider. We don't use bridge, we use voltage divider. 1, 2 resistor plus amplifiers. The last one is the power dissipation, will be similar, same concept. This resistance, this sensor will be energized, so it will self-heating. Same thing. So, for example, if how many? Okay, in this example, the PD. What is PD? PD is a dissipation constant. Five milliwatts per degree. 5 milliwatts per degree. So that's PD. Dissipation constant is 5 milliwatts per degree. And the amount of power, they also calculate the amount of power, is the voltage squared divided by resistance. Voltage is 5. It happens to be 5 here. So 5 squared divided by 3,500 ohm is 7 milliwatts. So if the resistor power is 7 milliwatts and the PD, the dissipation constant is 5 milliwatts per degree. That sensor will be 1.4 degree hotter or warmer. So if the temperature is 20, again 20, the measured temperature will be 21.4. 21.4. It will be 1.4 degree higher above the measured temperature. All right, so that's a problem. Self-heating is always a problem. How do we reduce the self-heating? The self-heating is can be significantly reduced if you have a good heat sink. So you do not have your sensor in a very close environment where that energy cannot released to the environment. So if so that can be reduced. So those are the first two. Most commonly used are those tools in the industry. The first tool is probably okay. I repaired a stove one of my stoves doesn't work. I checked it out. The temperature sensor is RTD sensor, and it basically tells you how much the resistance will change when the stove goes from room temperature to 400 degrees, for example. So those are quite popular. In the industry, also these are more popular. Thermocouples. So what exactly is thermocouple? Thermocouple is put it this way, is a small battery. It's a small battery. It will convert thermal energy into electrical energy. So that's a thermocouple. It's a little battery. When this little battery is warmed up, it will create electrical power. The electric power it created is really very weak, milliwatts. The voltages it created in the milliwatts. It's not like a battery we familiar with, this battery, 9 watts. The output between the positive and negative, 9, positive 9. Now that's thermocouple. Define the different types, type K, type S, type J. Type K is most common. It's a type J. Type K. Type K is more common. If you look at this slope, yeah. Type K is based on these two metals. That's the material to build a type K. Type J will be a different type, iron and a constant 10. So different type have different range. Look at the range of K. Negative 200 to positive 1200. So it's have a significant wide range. That's why, because in the industry, a lot of time you need to measure above 700 degrees Celsius, maybe. And when you want to measure above that temperature, the thermocouple will be a perfect choice. 1500 degrees Celsius. So thermocouple, the output is the voltage. The output voltage. It's milliwatts. And the sensitivity actually varies. This one is the most sensitive, type J. Type S is less sensitive, but by being less sensitive, type S have a wider range. 1500 degrees Celsius. So can handle higher temperature. So you probably will pick different types based on the application requirement. Just like a battery, the thermocouple is have polarities. One is positive, one is negative. Unlike the previous one do not have polarity. It's just a resistor, so it doesn't matter which terminal connect to which. The thermocouple, on the contrary, when you're using a thermocouple, make sure the positive and negatives goes to the right positive connection to the right negative connection. So So sensitivity, let's use type J. 0.05 milli per degree. That's your sensitivity. Sensitivity of type J. Type S is even worse, 0.006 milliwatts per degree. So that's your sensitivity. When temperature goes up 1 degree, it doesn't, the output voltage doesn't change much, very little change, nearly 5% of 1 milli. That's 50 microwatts, 50 microwatts. Very small voltage change. The construction of a thermocouple is, because it's built metal, so it's very tough. So construction, just like RTD sensors. Range will be depend on types. So whatever types. For example, type J and type S. Type J will be negative up to 700, right? Type S will be 1500. Positive. Time response, it's almost the same. Time response will be, oh, where's my range? I put it wrong column. Range is 700, 1500. The time response is a second, 10 seconds. Again, 10, 20 seconds. The author says, however, the author has a lot of industrial experience, which I do not have a lot of industrial experience. So we just follow the author's. So the author said, however, thermocouple made of small gauge wires can handle time constant as high as milliseconds. So it looks like the time response is all depend on how you build your thermocouple. So if you build your thermocouple with very small gauge wires, physics, it's all about physics. You have a less of a physics mass for the thermal energy to transfer. So the time response goes very fast. That's something nice to know, yeah. So if you want to fast response, you use a small gauge. You need 2 different type of wires. For example, type J, you need one wire made of iron, the other wire made of constant 10, which is a copper and something else combined together. It's a combined metal alloy material. So if you build in those thermocouple, you have a choice to use the gauge, small gauge iron, small gauge constant 10 wires. Make that time response faster. So that's response time. Next will be the signal conditioning. Because it's voltage, it's all about amplifier. So we all need amplifier. We don't need a bridge. We don't need the voltage divider. The output is voltage. And that's a perfect input for amplifier. So output already voltage. We don't need to convert. Previously, this part is converting to voltage. And then amplifier will recondition in the voltage. In the thermocouple, it's a little battery. The output voltage changes with temperature. So input is the voltage. Perfect in this amplifier application. Well, there is another problem. It's not perfect, but got another problem. For example, if you are using type J, you have iron. One wire is iron. One wire is constant 10. sooner or later, you need to make electrical contact with a different connector, probably made of aluminum or copper, whatever connector you will make. So you will create another thermocouple right there, right? Because anytime two different metal touch, it will be a thermocouple, anytime. So that can be a significant problem. That problem can be solved by a second subject called reference compensation. This is the problem. So if you have type J, you have iron, one wire is iron, positive. I may be wrong, maybe the iron is negative. Thermocouple is polarized. So one is positive, one is negative. Let's assume the iron wire is positive, the constant 10 is negative. So this is the iron goes to here. You cannot have iron go all the way to here. Sooner or later, you need to connect to your electrical board. When you connect to your electrical circuit, that's another thermocouple right here. And then you have constant 10 wire. You need to connect another connector. That's another thermocouple. And it turned out, if the temperature here is constant, all you change is the reference temperature. We call this temperature here reference. That is your room temperature, because most likely your equipment is room temperature, and that's your oven. So your oven is 400 degree. Your oven 400 degree didn't change, but the room temperature changed from, for example, in the winter is 30 degree, in the summer is 100 degree. So in the summer, winter, and that will cause the voltage to change, and your measurement will be off. So when you're using thermocouple, the reference point has to be keep constant. One way is put your equipment in air-conditioned room. Don't worry about it. Then you forget about it, because your equipment is air-conditioned room. It's 72 degree all year round. So that's reference will be constant. What happens if you do not have your equipment is outside? The temperature does change throughout the season. So in that case, you need a compensation circuits. Compensation. That is what we call reference compensation for thermocouple. That thermocouple is a little battery. Unfortunately, that little battery existed anytime two different type of metal connect each other. And that cannot be avoided, because sooner or later, you need to make connections to different type of metal, to different type of connectors. So that's the compensation. That problem is solved completely. Of course, you can control the environment, or another way to control is let's control your environment. Yeah, your room temperature constant, or you have actual circuits, or if you have your computer to do it for you. Anyway, there are many different ways. Just to be aware of this problem. It's called the reference point. You will have to keep your reference point stable. If your reference point is unstable, of course your measured temperature will be floating.
I think we do that with digital correction at ours. We use those a lot.
Excellent, Joe. Yes, tell us about it. How do you do a digital correction?
Well, we use these giant pressure cookers to cook cans, and we have to guarantee that the cans are getting to the temperature that we want them to, right? Yes. For food safety. Mm-hmm. So sensors are put in the can, and then wires are run out to an air-conditioned office, and we have a data logger in there that they all connect to. And so when we get new sensors, mm-hmm. they all have to be calibrated. Mm-hmm. And so they adjust for their natural tendencies digitally. And then that sensor receives a number, and it always is sensor number 1. and it always plugs into the same point in the data logger where its digital correction is. So we have to be really careful that they're tracked and they go in the same spot every time. You don't want to mix those up because then your digital correction will be off.
Yes, perfect. The computer is so powerful. Now everything is done by computer. That digital correction is a perfect example. For what I understand from Joe's description is every sensor has its own characteristic. So you make a compensation for the different characteristic of a different sensor by a lookup table. So the computer will basically look up a pre-existing table, pre-plotted the characteristic of your sensor, and make corrections for the variations. Is that right, Joe?
Yeah, that's exactly it right there.
Thank you, Joe, for the information from. Is that trade secret in your company?
No, this is USDA required food safety things.
Okay.
So it's not, this is done across the board anywhere anyone uses pressure canning.
Okay. So
be
you
it
can
dog
tell
food
us.
or yeah.
You can
it's
tell
not,
us I don't have to kill everybody.
no. They do have some fancy wireless ones, but you can't monitor them in real time. You have to extract them and then put them in and then plug them in, and so ours, are hardwired through the wall of the retort, and you can watch the temperatures in real time and see. And what they're looking for is, cold spots in the can. If something doesn't cook all the way through, you'd have a cold spot in a section that's not cooked, and so it's not safe.
Yes.
And so every food that gets on the shelf has to go through these tests to make sure that it's being cooked properly. And
Is that cat food?
cat food, dog food, but also any human food that a
Oh,
factory
you also
would
cook
do.
human food?
We don't know, but
okay.
human factories have to do the same tests.
Oh, okay. All right.
And it's all, you have to keep records, and it's all very precise. It's all directed by the government how we have to do that.
Thank you for my cat. We bought a lot of cat food. Two cats eat a lot of cat food. For some reason, we have a shortage of cat food. Sam's Club ran out of cat food, a particular brand. Maybe you guys need to work harder. So,
Oh yeah,
cook more.
they're
More cat food. The cat depends
right.
on you.
What brands do you guys make?
So I work for Purina, so everything from Friskies to Fancy Feast.
My
There's some
God,
of the
that's fancy feast. Yeah, we are doing fancy feast.
Yeah. The factory here in town works 3 shifts, runs 24/7, and they can't keep up with demand. They average about 1 million cans a shift, so about 3 million cans a day, give or take. And they can't keep up with demand.
So do you buy the cat food for your cat too? Which one you recommend?
Oh yeah.
They good?
I like the Fancy Feast and
Fancy feast. Okay.
Pro Plan for the dry.
We have a previous graduate. He works making sausages, and I asked him, "Do you eat the sausages you make?" Always nice to know. What goes into your sausages? Okay. Anyway, where were we? Very nice. Thank you, Joe. Nice chat. I almost fall asleep. Now I'm completely awake. Let's keep moving on. Yeah, nice to have, because when I talk a long time, I kind of get bored also. Construction, thermocouple, signal conditioning amplifier, dissipation constant. Yeah, we got dissipation constant too, because that's that sensor can be self-heating also. Maybe that's a problem than previous one, because previous one are resistors, so they actually self-heating significant. So it's probably not an issue here. Dissipation constant. So that's a thermocouple. I will give you an example of thermocouple interface circuits. We will not go into details, but just give you an example what it looks like. That's your thermocouple. That's your reference point. That's where the connections are made, connected. So you want to keep temperature where the connection made constant. Otherwise, you have to have extra circuits to compensate for the temperature changes right here. So this is a type J, for example. So one wire is on, one wire is constant 10. And then you make connection right here to copper wires, and then you don't worry about the copper all the way through. So that junction is the second junction. You want to keep that second junction connecting point in air conditioning in the room. All right, that's the sensor. Yes.
Oh, so you have the two different metals you said, and you have at that junction there, it splits off into two copper wires, you said?
Yes, that's right. It's iron to copper, constant 10 to copper, yeah.
Okay.
Yeah, most likely you are using copper connectors. And then you have a bunch of amplifiers to convert this. For example, this is a convert to 0 to 5. The temperature goes from 500 to 600. So the temperature measured by this thermocouple will change from 500 to 600 degree. So temperature 500 to 600, and the voltage will change from 12 to 15 milli. This type of sensor, voltage will at 500. That's Fahrenheit. Okay, I need to change that to Fahrenheit. Because it's Fahrenheit, that's 500 Fahrenheit. The voltage will be 12. At 600 Fahrenheit, voltage will be 13 to 16. So the voltage will be 13 milli to 16 milli. And when voltage change this little battery, and go through this amplifier. When input is 13, output is 0. When input is 16, output is 5. How can we do it? Very easy. If you remember one of the demos we did on multi-sim, yeah, that's one of the demos. What multi-sim input goes from 13 to 16 milli, up and down. Output goes from 0 to 5, up and down. So all you need is to change the resistors to make it happen. So that's thermocouple. The last problem with thermocouple is another problem in real world. That's noise. Because the input voltage, we are talking about millis and micros, and this sensor is always very close to a lot of heavy instruments, a lot of power, a lot of noise, electrical noise. And so it's very important to reduce noise. Otherwise, what you get here is all noise. It's not the temperature measured, but the noise, electrical noise. So it's very important to keep the electrical noise down. How do we keep electrical noise down? Very easy. All we need is a jacket, copper or stainless steel jacket. So when we protect the sensor, and we ground that jacket, so the noise cannot go into the sensor. Well, it will be great if you have this jacket all the way to here, but sometimes it's impossible or too expensive. So what happens after this protection? After protection, you have this bare exposed wire. In that case, we generally use twisted wire. Why twisted wire? Because if you do not twist it, for example, from here to here is 20 yards. Or 100 yards, or 1 yard, whatever distance between your cooker and your controller. That's your controller, that's your pressure cooker. And it might be 100 yards. Without twisting, all the noise will add up. This wire will act as an antenna. That's terrible because the antenna just pick up all the noise. Every noise will be picked up by those two antennas. So in order to remove the noise, we use a twisted pair. Twisted pair is the perfect way to cancel. So the noise accepted by one loop is canceled by the next loop. So you have a little bit of noise from here to here, collect it. It will be canceled out. Collect, cancel, collect, cancel, collect, cancel. So when you reach your destination, the noise you picked up by this little antenna will self-cancel, self-canceling. So twisted pair is a simple way to reduce noise. You can actually manually twist it, couple loops per inch, per feet, couple loops per feet, not per inch. Anyway, just twist it as close as you can. The closer you twist it, the better the noise cancellation effect. Ideally, you do both. You not only twist it, you also wrap it with the aluminum foil. That is another jacket to protect the wires. So very important to make that the thermocouple sensors reduce noise because the voltage are very weak. Otherwise, you will pick up radio signals, televisions, whatever power signals, 60 hertz. That's a huge noise, 60 hertz. So there are noise everywhere. You have to reduce that. Well, I said the thermocouple is a little battery. Actually, we use it as a battery. These are just one application of thermocouple. I have a fireplace. If you have a fireplace, actually, if you have a furnace, chances are you have a thermocouple inside. That thermocouple is actually used as a battery. So that thermocouple is called a thermopile because a single couple is not powerful enough. The voltage is 20 milli, for example. So you have a couple. We not call thermocouple, we call thermopile. This thermopile, just like this. If you look at this battery, the output is 9. Actually, if you cut it open, inside you have 6 1.5 battery. So 6 of them piled together. So this is a battery pile. This is a battery pile. We don't call it a battery pile, we just call it battery. But should be called a battery pile. It's a pile, like a same thing here. You have one single battery, 20 milli. What about you have 6 of those? 120 milli. What can you do with 120 milli? It turned out in the furnace, this 120 milli thermal pile is attached very close to the pilot flame. So you have a little pilot flame. That pilot flame, on top of the pilot flame, is right there is your thermal pile. That thermal pile will generate 120 milli voltage. That 100 milli voltage will open the valve of your gas pipe. So the gas pipe valve will be open. They call milliwatts valve. Milliwatt valve. So this valve can be turned open closed with 120 milli. So it's a safety device, just in case your pilot goes out. As soon as your pilot goes out, you lost that 120 milli, and the valve will shut off. So the gas will not leak into your basement, right? Without this, when you lost your pilot, if the valve is still open, and that can be extremely dangerous. So that's one application for the thermocouple. Usually $10. If you go to a thermocouple, you can buy a thermocouple from Menard, from Home Depot, whatever. $10, you can get one of those. All right, let's move fast. 1 hour already. The third type, the fourth type is called solid state. Solid state became so popular because it's semiconductor. Everything is electronics, everything is computer, and solid state will be perfect choice. Connect to a computer or build a IC. So everything is IC, integrated circuits. So solid state, this will be an example of solid state. That will be your temperature sensor right there. It's a diode. It's a diode. Another solid state. Yep. So that's a solid state temperature sensor. The current will change when temperature changes. That's the current. Or you can say the resistance changes. Generally, we say current or resistance. So this diode will let certain amount of current pass through. But as temperature changes, the current will change. And that will change the voltage. And that voltage will be reconditioned through a bunch of amplifiers. So that will be the complete circuit. You have your sensor, you have your amplifier. On Wednesday, we will do a couple of solid state. The reason, because we have those sensors. And those solid states are used local factories. For example, junction control, they use the solid state temperature sensor to check their battery temperatures. When they charge in their battery, they want to charge it as fast as they could. But there's upper limits. If you charge it too fast, your battery will become too hot and probably causing damage. So they want to keep an eye on the battery temperatures when they charging them. So they need a lot of those sensors. I was there. One of our graduates works right there as an engineer. So we were there, and they have dozens of those sensors. They don't put it in every battery, if I remember correctly. They put it maybe every 10 batteries. They have like thousands of batteries are charging at the same time in their plant. And they put those sensors every 10 battery, and they keep monitor those temperatures and then use the temperature to control the charging current. And they use the same sensor we will use this week, Wednesday, do the demo on the Zoom meeting. So same sensor. It's a cost. That sensor is probably 50 cents or less. So they use that 50-cent sensor. And then I asked him how much they buy. It's $70. So they actually paid $70. So that's 50-cent sensor. The reason they pay $70 is they buy it from a manufacturer. That manufacturer put a stainless steel jacket and some kind of protection around the sensor, and then sell them $70 a piece. So I was there because they were asking me if they can make those sensors themselves. So they don't have to buy $70. They just need to buy 50 cents, right? Same sensor. Why pay 50? Why pay $70?
So it's expensive because of the jacket that they put on it. Is that what you're saying?
It's expensive because somebody got ripped off. Yeah, that jacket is not $70 jacket. Yeah.
Okay, I didn't think so, but I was just making sure. Maybe they do something really special to it. I have no clue.
Yeah, it is special because they are actually dumping the sensors into the battery, which is a extremely acid. I don't know what kind of chemical. It's you never want to touch those, and that smells terrible. Also, the whole factory. Yeah, you are partially you're correct. Yeah, it's expensive because that jacket has to be. It's stainless steel. Yeah, stainless steel jacket.
Okay, so the stainless steel can withstand the acid.
Yes, that's right. Withstand that acid. They have to replace them pretty common. That's why they want to reduce the cost because $70 a sensor, they probably need to replace them frequently, and the cost goes up. And then when you buy car batteries, you have to pay, custom design. So yeah, and I met him later. So we cut open. So actually, he gave me the sensor. Said, "Why does it cost $70?" So together we cut it open, and I'm amazed. Inside is the same sensor we use in our lab, plus a resistor. So inside is a resistor plus a sensor. So it makes a 3-wire connection 2-wire. So it's converted to a 2-wire sensor. I will show how to make that conversion Wednesday. Anyway, the inside is not so. Once we cut it open, we know we don't have to spend $70 anymore. We will do 2 solid-state sensor on Wednesday, so that's our plan. Besides those 4 most popular, there are some also older types. The first type is this bimetal. Where is the bimetal? So the bimetal is this type of sensor. Everybody probably already know. It's different type of material. As temperature increases, they expand at different rate. One expand faster than the other. So if this top half expand faster, the strip will bend downward. Otherwise, it will bend upward. So this sensor used as a thermostat in cars, automobile, even for room temperature control. If you have the older type thermostat, it's mechanical. If you have the newer type, it will be solid state, even with Wi-Fi. For the newer thermostat, control your room temperature, will most likely be solid state temperature sensor or thermistors or RTD, plus some computers, so you can control your room temperatures from your cell phone that way. The last type will be the meter. The meter is also older. That's probably the oldest. The meter can be either vapor, can be gas, can be liquid. So that's the 6 different type of sensors. We spent more on the first 3. The next 3, the solid state, became so complicated it became a computer. So actually, when it became computer, it became so simple to use. 5-year-old know how to use it, use a computer. So it became easier. So we discussed different types of sensors, and we cover 1, 2, 3, 4, 5, 6 categories each sensor. And I kind of draw a table. So that's all I have for today. I will see you guys Wednesday. Again, we will do Zoom meeting about the lab. I have a pretty good idea what we want to do in the lab. We will do a project individually for a PID controller. So that will be our lab. Besides all the demos I have on the Zoom meetings, we will do a PID controller. Fortunately, this PID controller is very inexpensive, like $20 or $30 from Amazon. So why not we just buy it? Because hands-on is always the best way to learn. And this class, we talk about PID controller. So we will ask everybody to buy one of the PID controller. I will do it this weekend to complete the project, to finalize everything. I will use the household material, so you don't have to spend anything more on top of this $30. So I will need to buy this PID controller, $30. And everything else, hopefully you already have those around in your garage. And you put together a PID controller, and then we'll tune the PID controller. So that's our subject. So we will tune the PID controller, watch how it will respond with the P, I, and the D tuning. We will tune each parameters, the timing of integral, differential timing, and proportional band. We'll change all those parameters and to see how the controller acted in response. So that will be our project. And this is actually very useful. For example, you want to cook pizza, perfect, crispy. This PID controller can control your pizza oven up to a degree, or even a fraction of a degree. That kind of accurate. Unless, so you will have the most accurate or fancy pizza cooker in your neighborhood. But we will not do it. I kind of I don't want you guys to handle high voltages. So when we do this project, we use a 12-watt system battery because safety is more important than everything else. So we will use. So that's why I will do it. I actually have 120 already, but we will scrap that to do a 12. So. All right, that's all I have for today. I will see you guys on Wednesday.
Dr. Zhang.
Yes.
Were we ever planning on having one of those labs outside of Wilson? Because I know you had talked about that at the beginning of the semester.
Because the situation changes. So that's what I'm thinking, just doing this. I will spend a couple of weeks, everybody doing their own at your home. So you don't have to go to Wilson.
Okay.
Go to Amazon. Let me show you the controller. Anyway, I'll show you Wednesday. The PID controller, and we will probably use a 60 watts light bulb as a heating element I will do it this weekend to make sure everything works before I formally decided we want to do this, go this route. Okay.
Does anybody still have 60-watt light bulbs that incandescent?
Yeah, I will sell $10 each for you guys if you don't have one. Or $70. All right. Yeah, I threw them all away like trash. Yeah. Don't throw it away.
One from my mom. She's got a stockpile of them.
Yes, I actually a couple of weeks ago I went to my basement. Amazingly, I found I'm still have one of two in my basement. Some of those lights are never turned on. I realized they are 60 watts.
No, when that ban went in, my mom bought all the 100 watters she could find. She has dozens of them in her basement.
Why your mom want 100? You want to keep the basement warm, right?
Yeah. She didn't like the fluorescent bulbs when they came out, the CF.
Okay.
Yeah.
Yeah. You know, we do a little, let me turn off the recording. Stop. Where is the recording? Stop recording. Okay.